Hello and welcome to JHEP's lesson on complex ions. This does cover a lot of stuff, of which it is labelled below. So have a look at the description. So, one thing about transition metals is that they can form complex ions, and we're going to delve deeper into that because what actually is a complex ion? Well, this is what a complex ion looks like. This is iron when it's been oxidized when you put it in water, and as you can see here, we have got water molecules attached to this iron, iron ion. Weird. Anyways, and as you can see, they have donated electrons to this ion over here. Okay, I know it's going to be really difficult because it sounds the same thing. Iron. I'm just going to point to the ones which I'm talking about. So it's pointing, the water molecule is donating electrons to the ion. So you might not be able to see here, but these electrons over here are lone pairs, and these have donated its only lone pair. So that means these things, these water molecules, are therefore called ligands. Okay? It may seem like a foreign word to you, but a ligand is a molecule or an ion that donates its lone electrons, its lone pair of electrons, to the central metal ion. And as you can see here, it actually has donated it. And we've got 6 of them to form an octahedral structure, all with a bond angle of 90 degrees. This is AS chemistry. You should really look that up if you're doing this as well. We've got 6 of them, and they form, ligands do form a dative covalent bond because they are given both of its electrons. It's not, well, not given, but it's sharing both of its electrons. It's not taking any. It's not being shared from any, from the, the ion. So another word for that dative covalent bond that we love to call it here is called a coordinate bond. Okay, a coordinate bond or a dative covalent bond are the same thing, but we use coordinate bonds when we're talking about transition metals. So, as we can see here, we've got the central metal ion and we've got the ligands. So a complex ion is a transition metal ion which is bonded to one or more ligands by coordinate bonds. And the ligand is a molecule or ion that can donate a lone pair of electrons, pair of electrons which are transition metal ions to form a coordinate bond. So as you can see here, these water molecules have donated only one lone pair of electrons. It can actually change. We can actually have more than one. But let's not go into that so far. So the way that we would write this is square brackets, the ion first. So we've got ion. And then we've got 1, 2, 3, 4, 5, 6 water molecules. So we write H2O and then 6 at the end of it. Close bracket, and then we've got the charge on it. Okay, remember this is an iron ion, so this ion is actually 2+. These water molecules are neutral, so the whole complex ion will therefore be 2+, and we do need to write it with these square brackets at the top of it, over here and over here. Okay, so as you can see, Fe, we are using Fe2+. We are using an Fe2+ ion. Usually, sometimes, some ligands can be ions. They can be Cl, and that means those ligands will have a charge as well. So let's say we've got FeCl4. Right, these chlorine ions will have a charge of -1 because if we look back at our periodic table, we will find out that the oxidation number for any number which is in group 7 is minus. So we've got 4 we've got -4 in total here. And seeing as we have Fe2 plus, that is going to be, well, it could be an Fe3 plus. We'll make it Fe3 plus. That'll be a +3. So that means the overall charge on this ion will be minus. Looking at this complex ion, we can see that we've only got 4 chlorine ligands connected to this ion. Okay, I did say that over here. Yeah, and the way we would write it is FeCl4 minus. Okay. Again, what I've done here, what we've used here is Fe3 plus. We've used the ion 3 compound instead of ion 2. You do need to learn the colours as well. Ion 2 is green. I mean, the way I'd remember it is that iron is green on both sides of the pond. And Fe3, that doesn't really make sense. And Fe3 plus is going to be a kind of orange, rusty colour, especially when it forms a precipitate. So we've got the 4 ligands here connected to it, and we've got this structure is a tetrahedral structure, and we do also have square planars. There are a lot of them which are square planars, which do look like this. We've got the sorry about that, and we've got the ligand here. We've got ligand here, and ligand here. Okay, it is very good if you are able to actually imagine this on a piece of paper. It does you justice a long way, a lot of the way. In the exam, you do have to draw these things. You do need to name the structure of it. You do need to remember that, and you do need to remember the bond angle as well. Right, so some ligands do have the ability to actually donate 2 or more lone pairs of electrons, especially this one, which is ethane 1,2-diamine. And as we can see, it looks like this. Oops. It looks like this. We've got the nickel, and we've got the ethane 1,2-diamine over here. We've got 3 of them. And as you can see here, if we just separate this ligand, oops, okay, that wasn't very clever. Ugh, that wasn't clever either. So if I just group this, so this is a ligand. Okay, it is connected to 2 bonds, 2 coordinate bonds, because it does give off 2 lone pairs of electrons, so it will give 2 coordinate bonds. So this is an ethane 1,2-diamine ligand over here. Nothing more to say about that. We've got 3 of them over here. We've got 1, 2, 3, and the best thing about complex ions is that it can actually form stereoisomers, and that is also another thing that you need to look up on in AS chemistry. Again, bidentate ligands are molecules or ions which have the ability to donate 2 lone pairs of electrons to the central metal ion. We do have more. They can be more, like EDTA, that will give off 6. That is called a hexadentate ligand. Or another word for it is a multidentate ligand, because it gives off more than 2 lone pairs of electrons. So moving on, ligands can actually be substituted with another compound. So say for example, we've got this copper 2. Oops, sorry, I don't know why Fe is there. We've got this copper 2 ion over here, molecule over here. That's supposed to be Cu. And we've got 6 ligands connected to it. If we add an excess of ammonia, NH3, yep, of ammonia, 4 of the H2O ligands gets replaced by these ammonia ligands. So 1, 2, 3, 4, and it looks like this. Okay, another way to write it is CuNH3 4 H2O2. This basically tells us that there are four there are four ammonia molecules and there's two water molecules. Okay, seeing as ammonia is neutral and so is water, the overall charge does stay the same. But obviously we do have H2O. You do need to learn the colours for it. You do need to learn that if we are substituting ammonia into aqueous copper, it does make a deeper blue solution. You do need to learn that. But a good thing about it is that it can actually form different isomers of each other. So there are two types of stereoisomerism that you do need to learn. There is the cis-trans isomerism and there's the optical isomerism. The cis-trans you have met before in F322 biology, in chemistry. And as you know, stereoisomerism are species with the same molecular formula but different spatial arrangement or different arrangement in space. And as you can see here, we have got two water molecules which are close to each other, so we call them cis isomerism. The way I like to think about it is that they are sisters, they are close to each other. It might not be a good idea, but that's the way I remember it. And as you can see here, these are far away from each other, so therefore they are called trans isomerism. And as you can see here, the molecular formula are exactly the same, but you can see here that the arrangement in space are totally different. Okay, usually when they give you a usually this can come as part of a 10-mark question. Do write down what this cis-trans isomerism is. With optical isomerism, although it's actually quite harder to do, but optical isomerism would only work when you've got bidentate ligands or a mixture of bidentate and bidentate and monodentate. That's the other one. Monodentate. Mono means one, so monodentate ligands give off one pair of electrons, one lone pairs of electrons. And as you can see here, if we just flip this like so, I know the letters have also flipped, which is not really the best, but as you can see here, these are non-superimposable mirror images of each other. Non-superimposable means, I'll give you an example. If you put your hands on top of each other, you can see that they don't actually overlap each other. They don't actually they don't overlap as nicely as it could do. And it's exactly the same here. If I place this on top of that, it looks like a mess. Okay? And that's what non-superimposable means. They do not lay on top of each other quite nicely. I didn't write the definition here, but that is the end of complex ions. In the next video, I will be talking about ligand substitution when it comes to the body, and I should be talking more about the reactions and the colors. So as I said, you do need to remember the colors.